We have arrived at our last subject for this semester, and this is going to be about counters. And so, what are counters? They are sequential logic circuits which deal with the generation of sequential codes, that is, codes that change from one number to another. And we're going to find out that from our discussion today, counters can be what we call single mode, such as counting 0, 1, 2, 3, 4, 5, or multi-mode, up and down. We're also going to find out that they either are synchronized to the clock or partially not synchronized to the clock, what we call asynchronous operation. Outputs will be shown to be frequency division of the input clock signal, and we will also show that you can reset the counter by resetting all the flip-flops. So let's begin with the single mode synchronous counter. The single mode synchronous counter is appearing on the bottom here. And I might want to just point out again, going to our quiz number 10, that question number 1, which is going to appear on the final exam, is going to ask you about these 4 different types of counters. Now, I'm showing you a synchronous counter. You can see that this diagram is the same as this. But be aware that I could also ask about last video's subject about the data latch register or the shift register, or in a few minutes, the ripple counter. So be aware of these 4. I will not ask about the up-down counter on the final exam. Okay, so just be aware of that for quiz number 10. So let's take a look at this circuit. You can see that the architecture consists of an array of JK flip-flops. They're configured to, first of all, they're driven by a common clock line, so that makes them a synchronous sequential logic circuit. And they're configured to either work in the toggle mode or the no change mode. Toggle mode or no change mode. So let's see how this works, and I'm going to show this last sentence here. This is the key here to how the circuit works. This circuit toggles by ANDing preceding ones in prior positions. So let's see what we've got going here. Well, first of all, I'm going to show a clock waveform here, which I could illustrate either left and right. But in particular, I'm going to show it going up and down here on this diagram just so I can get more information in. And the blue numbers are indicating the state of the count of the counter. So this is 0, this is 1, this is 2, this is 3. So let's take a look at this statement here. I'm going to toggle by ANDing preceding ones. Okay, so here's a preceding one. Well, first of all, let's explain the QA here. QA is operating in the toggle mode, so therefore it goes up and down, up and down, up and down, toggling. In this particular case, we have negative edge triggering, so every time there's a negative edge on that clock signal, it toggles. All right. The next stage is going to toggle only, notice that there's some gates up here, all right? It's only going to toggle when the preceding stage is a 1. So here's my preceding 1 here, and that's when I'm going to toggle over here. The third stage is going to toggle if the preceding 2 stages are a 1. Now I have an AND gate up here that can detect that, okay? And then the fourth stage will toggle, I don't show it here, but when the preceding 3 stages are 1, and that's detected by these AND gates up over here. So this circuit here is very interesting, and actually, if I just consider 2 stages, which is just these 2 flip-flops, that is your lab number 10. Okay, so this is how this one works. So let's show you an example of this now by going to the artboard. And let's look at the questions that will be looked at here. So this is I'm actually going to do question number 4 for you today, which you'll see on the final exam. Now, question number 4 is going to give you a counter with QA, QB, QC, QD, such as shown over here. And I'm going to ask you a question here. I'm going to say which of these waveforms corresponds to output QB. All right, so let's go to the artboard. So in this particular case, I've got this drawn out in bigger form. And so the rule here for doing this is to notice a characteristic that I was going to point out also on the notes, which is the process of something called frequency division. Look at the very top here. The outputs provide frequency division of the input clock signal. Okay? And so what you're seeing here on this is that every waveform over here has half the frequency of the successive stage. And then on the artboard, I'm asking you to sort that out. Well, here's the rules here. Right on the top, this is what you need to know for the final exam. That if I give you a clock sequence up over here, that the first flip-flop, QA, is going to have twice the clock period or half the clock frequency. Okay? So you can see that QB2 has twice the clock period of the original clock. All right, so that would be QA. But in this question, I'm asking about QB. Well, QB will have 4 times that. All right, and so let's see which one that could possibly be. Looks like this one here. 4 clock periods between this point and this point. Now, this is 1 period of this waveform. This is 4 times the length of this distance here. So therefore, QB4, the answer to this question is equal to QB4. Now on the final exam, I can ask about any of these, A, B, C, or D. Should I ask you about QC, the answer will be 8 times. So this one here is going to be 8 here. And then should I ask you about QD, then you're going to have to get this answer, which is going to be 16. All right, 16 TC. All right, so those are going to be the answers that we'd have. So let's take those answers off here just temporarily, so I can ask you a question and see if since you typically can't remember what I did 5 minutes ago. So, but I did just show you the answer. Here's an example question that I could ask on the final. All right, so this question is asking you to find QC. All right, so can you remember what I just showed you? Which one of these is going to be 8? That's the question here, okay? So you'll have to remember the sequence of 2, 4, 8, and 16, which is easy to remember because this is also, when you do a Carnot map, when you circle 2 1s, 4 1s, 8 1s, and 16 1s, kind of remember that same sequence. So as I just showed you here, QC is going to be 8 TC between here and here. All right. QB3. All right, let's now finish up what we're talking about in the lecture notes and go on to the next type of counter, our last kind of counter. And let's do this one here. So this next counter is the simplest kind of counter. It's called the ripple counter. And basically it's an asynchronous sequential logic circuit because the clock does not go to all the stages of the flip-flop. It just goes to the first one. The other clock inputs are derived from the clock outputs from the preceding cues. All right. Notice that this point here, it's basically an array of flip-flops configured. Each of them are configured in the toggle mode. All right, toggle, 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 toggle. And successive flip-flops are clocked from the outputs of the prior flip-flops, as I just mentioned. So let's take a look and see how this one works. So here's the picture of this. Again, I'm drawing the clock going up and down so I can illustrate the operation. The count values are going to be in blue: 0, 1, 2, 3, 4, 5, 6, and 7. Okay, I'm missing my 0 here on the bottom. What we're going to illustrate here is that as it counts from the blue stages here, in between certain blue counts, I'm going to have a transient state. That is due to an effect that I call the ripple effect. So the outputs are going to change from the right to the left as the signal propagates through, because notice that the clock is only applied to the first flip-flop. That means successive flip-flops have to get their information from a prior stage. All right, and so this is called the ripple effect, because the clocks are delayed between the flip-flop stages, as it's showing you here on the bottom. All right. Transient states, which are green, appear between the stable states. So, for example, let's take a look at the count of 1 and the count of 2. In order to get from 1 to 2, I have to change 2 flip-flops, right? I have to change the blue 1 to a 0. Then I have to change that 0 here, which I showed in green, to a 1. So there's 2 steps here indicating that I have an in-between state called a transient state. And let's look at this example here from 3 to 4. In this case, I've got to change the first flip-flop from 1 to a 0, the second flip-flop from 1 to a 0, and then the third flip-flop from a 0 to a 1. So indicating that I've got 2 in-between states. These transient states only last for a fraction of a second, but nevertheless, they are indicating something that's going on between the state of 3 and 4. In particular, I go to states 2 and 0. So this is very odd indeed. Typically, a human can't see these transient states, but you can see those if you apply direct instrumentation. By the way, this ripple effect, where I'm going from the left to the right, from the right to the left here is also seen in the fall when you sit in a football stadium. All right. So, for example, this section here might stand up, and then this section may stand up, and then this section may stand up, and then the following section may stand up as you go around the entire stadium. So this is very similar to that effect. This rippling around the stadium is the same thing as rippling across the counter. So let's go ahead and take a look at this now. I'll give you this information here. I would like to illustrate this by giving you 2 examples for a 4-bit ripple counter. And these are taken from quiz 10. And I'm going to do them on the artboard, and then, of course, I always give you a third one to do as a iClicker type exercise. So let's go and look at this example. We're going to go down here. So this is actually questions number 6 and number 8 on that quiz, which are going to be done as follows. So let's give this a try. So remember what is going to happen. We're going to change each of these numbers from the right to the left. And here I've actually showed changing the first number. So then I'm going to carry the other numbers the same. This would be as if the first section of the stadium stood up and the rest of the section stayed the same as they are before. So let's do that. Let's keep these here the same. All right. Now the next section is going to change. So I'm going to change this one here, and everything else will stay the same. And then finally the third section, or the third output, will change. And now I finally arrive at the final answer. So in this particular case, in question number 6, I've got 2 states, 2 and 0, that appear. Okay, And so in question number 6, it asks you to identify these two states. In question number 8, is a very, very similar question, but it just asks how many states, transient states, are there in between here. All right, it doesn't ask about specifically what they are, but how many they are. Well, you still have to compute them out the same way. So we're going to change, starting with the first flip-flop, from 1 to a 0, keep the other ones the same. Change the second flip-flop, 1 to 0. By the way, it doesn't have to be changing from 1 to 0. It could be the other way around as well, from a 0 to a 1. Now we're going to change the third one, and then finally we change the last one. So the answer to question number 8 will be there are 3 transient states. Now please do not include the first and the last ones here at all, okay? There are a total of 5, but 5 is not the answer to the question. The question is how many green states, transient states, are there? And so be careful about that, as many students will put down 5 as the answer of the number of transient states in between. Well, let's go on to our iClicker exercise. I'm going to give you this one to do. All right. Oops, a little shifted up there. And so let's bring this one down and align these up with the others. There we go. So let's go ahead and halt the video just for a second. I would like you to tell me what the contents of the states are in between the count of 1011 and 1100 is. Okay, so let's see what did you come up with here. So let's go ahead and subtract these out here, and we will fill these in. All right, so you should have changed the first one to a 0, keep the other ones the same. Change the second one to a 0, keep the other ones the same. And then the third one is going to change from a 0 to a 1. So it looks like the answer is going to be, and then if I keep the other ones the same, I will have 0, 0, and 1 here. So it looks like I have 2 states, and should the question ask how many there are, the answer is going to be 2. Should the question ask what are they, then these will be the answers that you have. So that takes us then and completes the information associated with quiz 10. And I'll come back with an audio message giving you a little bit more details about what to expect on the final exam. But in any case, this is the end of the material for our course, and so be looking forward to hearing from me shortly concerning what to expect on the final exam in terms of exam 1, exam 2, and quiz 10.